Yes, so hello everyone. I'm happy to give a talk today about the AI-enabled molecular discovery of organic photovoltaic materials, and I'm Seungjoo from Professor Charles Schroeder's group. So organic photovoltaics, which is also called as OPV, is a well-known energy harvesting device and is applied to many kinds of things, such as, for example, it can be attached to the curved surface of architectures or buildings, and also even it can be applied to some flexible organic electronic devices, and also some vehicles. And also, it is known as it has some several advantages compared to conventional solar cells. For example, it has a low cost and ease of processing, and also it has a lightweight and high flexibility and semi-transparency. And because of these strong points that OPV have, many research has been done before to more improve and enhance the performance of OPV. For example, efficiency or the stability of the material, which are very important parts in OPV device. So OPVs are generally typically constructed with bulk heterojunction layer. So you can see this layer between the electrodes. It contains a phase separated acceptor and donor layer to increase the interfacial area, and increasing this interfacial area is very important because when the excitons are generated by the light source, it travels all through this interface, and in this location, the charges inside the excitons are separated, and minus charge goes into the acceptor, and plus charge goes into the donor layer, and they transport all through the electrodes, and the power is generated. And here are some typical donor and acceptor materials. And in this research, we are interested in this kind of organic materials using these layers. Our goal in this research is to overcome some typical difficulties in commercializing OPVs. And the most important and quite demanding difficulty that we must overcome is achieving the high efficiency and high stability at the same time. This is a high demanding part that we must overcome, because as we can see in these two examples, which are research that have been reported pretty recently. So the upper research has reported very high efficiency, but it had no stability data. And also the bottom research reported very, very long lifetime, which is related to stability, but reported very low efficiency. So we made a 10-10 goal, which is developing new OPV materials to achieve 10% efficiency and 10-year stability at the same time. And it has been never achieved before. But prior to achieving this goal, we must first deal with some typical challenge that we usually face with this kind of molecular discovery process, because this process is usually based on some daunting trial and error approach without a clear understanding of structure and property relationship. So to overcome this challenge, we are leveraging this closed loop material discovery process, which is a very collaborative process between three teams. So we start from this AI team. So they will use some AI methods to suggest a batch of promising OPV molecules, and they will send this data to the synthesis team, and synthesis team, which I belong to, will synthesize these all molecules through the automated processes, and synthesized molecules will be sent to the sent to the characterization team, and they will measure and calculate some properties that are related to the efficiency and stability. And this data will go back to the AI team, and this closure process will be repeated until like we reach our goal. So because I'm part of synthesis team, this talk will be a little bit more focused on the synthesis process. So for the synthesis team, we are leveraging two kinds of strategy to accelerate this closed loop process. So first one is we are using automated chemical synthesis process, which is based on the iterative Suzuki coupling method, which is an analog to a peptide synthesis. So if you see this figure, this monomer, which is also called a building block, is first deprotected, and it will react with another halide building block, and then we will get this dimer building block. And this dimer building block will be deprotected again, and then will be coupled with this halide building block again. And this process can be repeated until we obtain the target molecule that we want to synthesize. And all this process will be done in this custom-built molecule maker, which was built by Brook and Schroeder group, and it has fully automated synthesis process. And the second strategy we are using here is donor fibers acceptor molecular design strategy. So this is very common in OPV field, but traditional research, like past research which use this kind of molecular design has only dealt with a limited number of structural patterns. And this means that there's still large area of unexplored molecules in this OPV field. So we are using three kind of approach to investigate through this large unexplored area. First one is Lego kit approach. So this Lego indicates each building blocks. So it means that each building blocks can be substituted to other building blocks very easily, because we are using Suzuki coupling chemistry, which is very well known and very amenable to our molecule maker. And the second strategy is using a common donor fibrous moieties, because we want to have a part that for sure introduces the OPV nature to the molecule that we're going to synthesize. And the last one is diversifying the acceptor building block as much as we can, because we want to investigate through the large area of unexplored OPV molecules. And so, like for example, we brought up this molecule to the acceptor library, which is usually used for the cancer drug, and it has never been incorporated into these OPV molecules. And we have a couple of like more acceptor building block that is interesting like this. So by leveraging these two kind of strategies, we started with generating donor fibers dimer molecules. First, we searched some common OPV building blocks, and also we consider some synthetic availability, and it converged into this 22 donor fibers molecules, and we successfully synthesized all of these. And now we moved on to the acceptor building block, and we just picked 1,000 commercially available halides and went through some DFT calculations and some diversity algorithm. And we converged into this 100 acceptors, and that means that we generated a molecular library of 2,200 molecules. So based on this molecular library, DFT and RD kit simulations were been done with these descriptors, and based on these descriptors, all the molecules in the library were placed into the diversity algorithm, and AI team picked a batch of 10 molecules that has maximized diversity. And these are the 10 molecules that were suggested for the first round. And 6 molecules were successfully synthesized from this set. And these molecules were handed to the characterization team because the next step is the testing method. And the characterization team went through some UV-vis measurement, and based on this data, they calculated T80 and spectral overlap values, which are related to photostability and efficiency, respectively. And this data was sent to the AI team, and based on these observations, Griffin and Chimera, which are known as optimization AI method. AI team used these two kind of tools to suggest the round 2 molecules, and they came up with this 12 target molecules. And the synthesis team again synthesized the 7 molecules, and the 7 molecules are now also handed to the characterization team. Yep, and yes, so we are now moving on to the batch 3, and this means that we are in a third closed loop process, and we're very excited because there are many things to overcome to make this closed loop work smoothly. But we think we are now rolling very smoothly. And yeah, and for this project, we also have some 3 long-term goals. First one is to accelerate the synthesis by automating the whole process, and also we are planning to construct a solid relationship between the molecular structure and properties. And third one is kind of potential goal. So we'll also try to build up a purification and solubility data that from the synthesis all the synthesis that we are doing in this project. And based on this data, we think we can make some prediction model for a purification method and solubility for the new molecule. Thank you to all the PIs who guide us, and thank you to all the colleagues who work together very actively. Yeah, and I'm happy to take any questions.
Nice talk, Seungjoo. So what do you, since you've been on the front lines here and making the molecules, so what's been the biggest challenge on the synthetic side so far? And how have you overcome that?
Yes, so because the molecules were recommended by maximizing the process of maximizing diversity algorithm, maximizing the diversity. The suggested molecules had very different properties compared to each other. So I think that made the purification method for each molecule pretty tricky. So the synthesis team kind of worked on purification method. First round, we put many times on the purification method, but now I think we are adjusting and getting used to these molecules. So yeah, I think we're getting faster and faster. And also Nick and Eddie, part of synthesis team, they are trying to we are trying to automate the final purification method, which is connecting the automated machine with the LCMS or prep LCMS or the column. So we believe that could also solve many problems of this closed loop process.
Awesome job. I haven't actually thought about this. Do the molecules that can't be synthesized, do they have anything obvious in common?
You mean like what could be the thing that?
I mean, if you, as a synthetic chemist, you look at them, is there a reason you say, oh, okay, yeah, these aren't purifiable or synthesizable because of X?
Well, on experience that we had until now, based on the experience, the molecules that have kind of a long output chains, which makes the solubility of the molecule more better. So that kind of molecules were mostly purifiable, but the molecules that had only like aromatic building blocks, those are mostly hard to purify it. Maybe it could be the solubility problem or something. So
okay, yeah, I just wonder if in the future we could start thinking, since log P is one of the metrics, should tell you how hydrophobic the thing is. So you could, I'm just curious if the ones that failed all have like high log P or something, but something for us to think about. Which are very cool though. Yeah.
Yeah, thanks, Seungjoo, for the great talk. And also thanks everyone for the discussion today, I think. We can move next door to the in-person poster session. And you can enjoy the snacks and the drinks while you chat with students. Also, don't forget to cast your vote for the top poster today, and we will announce the winner tomorrow. Also, for people who are joining us virtually today, we will see you tomorrow at noon Central Time. Okay, thank you.